Good morning. All 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13 out of 27. Yeah. So what happens when I don't give assignments, I guess? Not even half. All right. And hey, today's the exam review day, so maybe I press pause and just give the students in class the benefit. Okay, so today we're going to be going over the principle of locality, some fundamentals of memory hierarchy, and we're going to be discussing how to calculate something called average memory access time. And then we're going to do an exam review because the exam is 1 week from, 14. We have the exam review is 1 week from, the exam is 1 week from today, the exam review is today. Also, your project 3 is due Sunday. I wanted to say really quickly, I've had a few groups come to me and ask questions about timing. They're getting weird results, especially with like shift left and shift right. Make sure that the clock that you use to test your element is running slower than the worst case delay. So for example, if shift left logic, you do 125 nanoseconds. If you do it slower, you're going to screw up the timing, and you'll get bad results. So make sure that it would be at least 125 nanoseconds. One student came in, I switched it to 250 nanoseconds, and it worked perfectly.
You switched the clock or the...
Yeah, the clock in the test bench. Yeah. So not the actual physical clock to dictate it, but the actual just like when you're timing it. Because if you're running it at 10 nanoseconds, it's going to update every negative clock pulse. So then they're going to get weird results on the output. It'd be hard to. But then if you do it, so when you get to the final project, the first part of the final project is you're actually going to be laying out the final result, the full data path, and then you're going to be calculating the clock that you're going to require in order on your project based on the, now that you're familiar with instruction memory and data memory and registers and the ALUs, you're going to add all of the stages up, and then you're going to find out, all right, my clock length has to be this in order for it to work properly. If it runs faster than that, you're going to get bad results. So this is why I've had you insert delays in the entire time, because you need to understand how clock length affects computing performance. And then I want to have a very brief academic integrity discussion. All right, so the principle of locality is defined as a program tends to access data that forms a physical cluster in memory. Multiple accesses may be made within the same block. And then there's two elements, temporal locality and spatial locality. Think temporal is time and spatial is space. If an element is referenced, then it's going to tend to be referenced again soon. For example, if you're writing code and you have a variable and you use the variable, right? You don't just write, you just have the variable, you use it once and then you never use it again, and you do that regularly, right? You actually are going to try to use the variables consistently in order to make an algorithmic calculation. So if you think about the sign multiplication algorithm, which may or may not be on your exam, you're accessing the product and the multiplicand variables in memory often. You're doing the same thing with these registers. The idea of these fast registers is that you're taking advantage of these 8 save variables and then the 10 temporary variables in order to perform fast local operations in order to take advantage of this concept of temporal locality. And then spatial locality is when item is referenced. Items whose memory addresses are close by will tend to be referenced soon. But for example, arrays. You access one element of the array. You're not just going, okay, well, I have this array of 10 elements, but I'm only going to access one. If you're going to create an array of 10 elements, you're going to eventually want to use all 10 of them. So that's spatial locality. So I would expect 5.4 to be on your exam this coming week. That's an important concept, as our computer science student has indicated to the rest of the class while you weren't here. Let me go back up here. So 5.5 is memory hierarchy. So now, up to this point in the data path, I've told you that the data memory is this big box, and it's a scary place. And we just have to know we could do a load operation, we point at it, and magically we get a 32-bit result. Well, today we're going to start going into that box a little bit. So the idea of memory hierarchy for 5.5 is a structure that uses multiple levels of memory in order to improve memory access time. And the reason why this is important is because these lower levels of memory hierarchy, your level 1, level 2, level 3 caches, are start out fast with the very fast registers, then you have a slightly slower level 1 cache, slightly slower level 2 cache, even lower level 3 cache. But as we're going up, the size of the amount of memory in there is increasing. And then we get to data memory, your non-volatile memory, and your disks. So here, this is a diagram that shows a good example of it. As the distance from the processor increases, so here's our processor, local registers, you have your small memory elements, and then the cache gets bigger and bigger. And then you have magnetic disks where you have your non-volatile memory. But it can cost up to, it can be 100 times slower than your typical cache. Now the big issue is, why would you do this? Why would you just want slower memory? Why would you want levels of hierarchy? Why wouldn't you just want the entire computer to be fast cache memory?
Would you get race conditions?
Not necessarily. I mean, these are good guesses, but
it costs way too much.
Bingo, there it is. Cost, right? These fast registers cost money. So there's magnetic memory, and then you're talking about your RAID arrays for disks, which is what you're using in your modern computer. But these are cheap. They're large but cheap. Small but fast. 32 registers, that's it, right? And you're doing that, you're using some of them for arguments for functions, you're using some of them to be able to do the global pointer and the stack pointer, you're using some of them. We're going to be learning in section 7 about exceptions and interrupts, what happens if we get bad information into the data path. You're using all that, but it's very small. And then your level 1 cache is a little bigger. So it's going to contain all of those elements for those 32 things that you have in your register, plus some other information. So you do something called memory swaps. You do that doing load and store operations at that level. And then level 2 cache is a little less expensive, but a little bigger. It has everything in there from the level 1 cache, plus other information that you would swap in. So as you're taking advantage of the amount of information you have in the different levels of cache, they tend to form clusters. And then that's when you want to perform swaps of blocks within those levels. If it's determined I need this, I need to get this down into level 1 so I can perform load and store operations, right? If I'm not using this amount of memory in level 1 anymore, then I want to put it in the lower level of the hierarchy, so that way it's, we want the information that we're using the most recently in the higher levels of cache. Does that make sense? So that way, this is a good compromise between speed and cost. And that's very important because ultimately you're going to be designing something that you're going to want someone to pay for, right? Because you want to pay for it because light doesn't pay for itself. So, went a little too far here. All right, so the cache memory for 5.6, the level of memory hierarchy between the processor and main memory, and it's used to take advantage of temporal and spatial locality. In 5.7, the block is the minimum amount of data transferred between cache and main memory. So for blocks, let's talk about the difference between data memory and registers. What is the size of the blocks in MIPS? Yes. Why is it 8 and not 32? Exactly right. Byte addressing, correct? So what's going to happen is it's transferring in 4 8-bit blocks. Now what's going to happen is where those blocks are assigned in different levels of cache, we're going to get to this concept called direct associativity and set associativity. Where you're going to be putting blocks in different elements. For those of you who've taken operating systems, you have to optimize where you're going to be putting the memory elements in the memory. And you do that by, here we limit it by 8-bit blocks. I won't scare you guys with the concepts of internal and external fragmentation quite yet. So this is what I was alluding to earlier. So you have the processor here. This is, where all of your ALU and instruction memory and access to data memory and your control units, everything you're designing in your final project is here at the top. So this blue represents the minimum amount of information transferred between level 1 cache and the processor. So here, you get 4 blocks and transfer it using a load word operation, and store word operation takes 4 8-bit blocks from the registers and puts them here in the cache. So here's the thing, level 2 cache, you're going to have a copy of it, right? Because you want to have duplication, because you're going to have, well, eventually when you get to your non-volatile memory, that's where you're going to have all of your information. When you turn the computer off, you don't want to lose anything, right? You want all of your information saved. So you have to get the information to be able to swap back and forth here. So the lower levels of hierarchy, in this case you got level 1, is going to be a subset of the level 2 cache, right? And then you're going to have different physical clusters of memory, and then you're going to swap them back and forth based on which ones you need more. So in section 8, we're going to be going over a problem called cache coherency. What happens when we're doing multi-processors and you have multiple levels of cache? I'm having one processor update one copy of a variable, but then I have another processor running in parallel, right? It's also using that same variable. So I have 2 copies in 2 separate registers in 2 processors. But I need to make sure that if this processor updates one, then the other processor doesn't update the incorrect value. See what I'm saying? We're beginning that in section 8. So we're going to be going over these ideas of cache hit, hit rates, cache miss, and miss rates. So a cache hit, it's the idea, if I go to level 1 cache, I'm performing a load word operation. And I say, do you have my information? And it goes, yes, I do. It takes 4 blocks and gives it to me, right? That's cache hit. We define it here as the requested data is in the cache. Read or write operation is performed directly in the cache without accessing main memory. Now, the hit rate is the probability that it's there. So this is something that you can perform calculations on. Over time, you can actually determine the hit rate of a particular cache based on the size of the blocks, your associativity levels, and the speed and the way you're taking advantage of locality. So it's going to be between 0 and 1, just like any other probability. The cache miss, so I go to load word. Give me this information. I go to level 1 cache. I don't have it. Sorry, it's over there, right? So then what's going to happen is you got to go to the next level of the cache. Am I here? Yes. And then you load that into the registers, right? So we're going to have 3 levels of cache in the problem. So I can go to level 1 cache and go, am I here? No. Level 2, am I here? No. Level 3, am I here? Yes. Okay, so it's in the cache. If it's not here, then we have to go to the RAID arrays and the magnetic disks, right? And that's what happens when you can take a long time, because then you have to go through the disk, you have to find, I won't scare you with operating system stuff right now, but every time I say one of those things, I see a couple of people saying, no, don't talk about that. I learned about AND gates earlier this semester. Okay, so the thing is like, how do we optimize the speed? And how do we calculate that? Because calculating computing performance is important when you're designing an advanced digital system. So cache miss is the requested word is not in the cache. So in this case, word is 32-bit. A block of words containing the requested word is brought out of cache, and then the processor request is completed. So you could actually say in MIPS, you can replace this definition with bytes. If the requested byte is not in the cache, a block of bytes containing the requested byte is brought to the cache, and then the processor request is completed. And then the miss rate is the probability that I'm not going to find it in the cache memory, right? And that's just 1 minus your hit rate. It's either it's there or it's not. So in order to calculate the amount of time, the average amount of time it will take us to say, hey, I need something from memory. You go in there and you find it, or you have to go to the different levels. Based on these probabilities, we're going to do a calculation called average memory access time. What is the average amount of time it takes for me to say, if Thomas is my level 1 cache, I say, hey, do you have my information? We can say 95% of the time he does, right? 5% of the time he doesn't, then I have to ask Lee, right? 80% of the time he does. If Lee doesn't have it, that means 20% of 5%, then I go to Enzo, who's my level 3 cache, and then 70% of the time he might have it. So 5% of 20% of 30%, then I have to go to Andrew, who is my non-volatile memory. Right? So what is the average amount of time that I would either have to just go to Thomas, or Thomas doesn't have to go to Lee, Lee doesn't have to go to Enzo, Enzo doesn't have to go to Andrew. What's the average time no matter what? That's called average memory access time. Okay, so 5.9 is just what happens when we just have a level 1 cache. So we're going to, these next 3 equations we're going to come up with, we're going to develop the equation for a 3-level cache. So given that TC is the cache access time, and we're going to call TM the main memory access time, and H is the hit rate, here's the definition. So the average memory access time, or AMAT, is going to be the hit rate times the cache time plus 1 minus the hit rate times cache plus memory. Now here's what this definition means physically. Hit rate, 95%. Actually, here's the problem, 95%. So for example, 5.1, we have a hit rate of 95%, a cache access time of 5 nanoseconds, and a memory access time of 100 nanoseconds. Find the average memory access time. So in this case, we're actually going to skip over Lee and Enzo, and we're going to straight from Thomas to Andrew, because Thomas is our level 1 cache. 95% of the time, so here, 95% of the time, he has the information I want, right? And it's going to take me 5 nanoseconds. But 5% of the time, which is 1 minus 0.95, I'm going to take 5 nanoseconds plus 100 nanoseconds, because Andrew's going to take 100 nanoseconds for my main memory, right? So I have to go through, I have to ask each person. So that's why this is TC plus TM. So it becomes 0.95 times 5 nanoseconds plus 1 minus 0.95, so that gives me my miss rate of 0.05 times 105 nanoseconds. And then from there, we perform a simple addition calculation, and we get 10 nanoseconds total. So what we want to do for 5.2 is now we go back into the Wayback Machine, and we're going to calculate performance improvement. Given a level 1 cache or the hit rate, so we have the same, determine the speed up over the same processor without cache. So now we don't have, so our processor with just Andrew, no matter what, every single time it would take me 100 nanoseconds to get the information, right? So now I've added this level 1 cache with a 5 nanosecond increase, right? So we calculate our average memory access time is 10 nanoseconds, right? So that means my speed up is 100 nanoseconds over 10 nanoseconds. So I have a speed up of 10 just by adding a level 1 cache, correct? So now we're going to build the second equation. What happens when I have level 2 cache? So the way it's going to work is the average memory access time is going to be 1 minus the hit rate 1. That's level 1 cache. So when I go there, instead of just going straight to the memory, I actually have to go to the level 2 cache now. So then that becomes 1 minus hit rate of TC1, which is cache 1, because I asked him, he says no. And then cache 2, he says yes. But then what happens when he says no? Then I go to the main memory. So that is this equation here. And so that's the average memory access time, hit rate 1 times cache 1, so that's my level 1 cache, plus 1 minus hit rate 1. So now we have the 5%. So now we're going here. So let's say hit rate 2 is 85%. So that's going to take me asking cache 1, then asking cache 2, right? And then, you see this is inside the bracket here. So this is a bracket. And that's a common student mistake on exams is to leave these off. Don't do it. In fact, I'll even make these like that so you can see the difference. Because think of it like a bracket, right? If we go to TC1, we will never need this information, right? But if we do, that means we have to account for all of this. So you're going to think of it, if you remember, have you taken probability of statistics? Yes, some, yes, no? Okay, so the general idea, I can draw it up here on the board. So we have 100% of all of our probabilities, right? So 95% we hit cache 1. So this is 0.95. So then here we have 0.05. So this is the second branch, which is represented plus 1 minus hit 1. So then from here it's 5. And here we either cache 2, which based on the problem 5.3 is 85%. So that becomes 0.85, right? But then there's this other 15% here. So that's 1 minus hit rate 2. And then from here, based on this problem, we'd be going to the memory, right? Now, if you left those brackets out, the calculation would look like this. And so instead of having all of the 0.5, you would have the 0.95, and then you'd have 0.85 here, and then you have 0.5 here. So 0.95 plus 0.85 plus 0.5 is definitely greater than 1, right? Because you have to take a path. So if we were, let me ask you a question. If I wanted to add a level 3 cache that had a 70% hit based on this branch, what am I doing here? Okay, so then, right, so this would be 0.7 and then cache 3, right? And then what does this become? 0.3, and this becomes memory. And then see, you have to make a bracket. You have to make a bracket at each level of your decision. So that's how you're calculating it. And just like you derived, we have our level 3 cache. So here we have our hit rate 1 times what happens when we go to the cache, plus 1 minus hit rate 1. So then this becomes our external bracket. That is our first branch. So then we have our hit rate 2, which we just shown. If we have to have this, that means we axe both levels of cache. But then what happens when it's not there? Then we have to go to this one. Now, this becomes our second bracket like you guys just discussed earlier, right? So then hit rate 3 times the cache rate 3 here. That should be there because you have to ask all 3. Make this all in one line, hopefully. Might not work. I'm trying to save space. There we go. Okay, so you have minus 1 minus hit rate 3. So this would be your second bracket. So we'll make that red so you can see the difference.
Plus 1 minus hit rate 3.
Yeah. There we go. That's correct. So you see how this is derived. Does this make sense how that happens? And you see how they kind of just cascades on each other? So if you just remember the pattern, and that's the reason why I have separate TGOs for 1-level cache, 2-level cache, and 3-level cache. It shouldn't just be mindlessly copying. You should see that there is a pattern to it. So that way, on next week when I ask you a question very similar to 5.4 here, you should be able to do it. It shouldn't be that terribly difficult, right? So here, the way it would be phrased is for 5.3. So the processor in example 1. So you have a level 1 cache, 95% or 99% hit rate in 5 nanoseconds, and then now we've added a level 2 cache with a hit rate of 85%, and the cache access time is 7 nanoseconds. And here, I'll get your question in a second. What is the average memory access time? So now we have same thing. We're building off 0.95 times 5 nanoseconds plus 1 minus 0.95 times. Now we're in our second branch. 0.85 times, that should say, oh yes, this is 12 nanoseconds, and the reason why is because it's 7 plus 5, TC1 plus TC2. Plus 1 minus 0.85, and this is 112 nanoseconds because it's 5 plus 7 plus 100. And then the rest of it is simple math. It comes out to 6.1 nanoseconds. So if you notice, by adding a second level, level 1 was 10 nanoseconds, right? Because we had 95% of it accessing level 1, but then we still had 5% of the accesses to the data memory. Now level 2, we had 99% accessing level 1, but instead of 1% accessing data memory, it now becomes 0.15%, because 0.85. So you see how by adding levels of cache, we're actually decreasing the average memory access time? So level 3, for example 5.4, and then we scroll down a little bit so people in the back can see. So the example in 5.3, we're given a level 3 cache, the hit rate of 80%, and a cache access time of 10 nanoseconds. Find the average memory access time. So now we've added our equation here. So now we have, again, 0.95 nanoseconds. This becomes 5% of the level 1 mesh. So I have 85% hit rate in level 2, 12 nanoseconds, 7 plus 5, plus 15, 0.15 here, 1 minus the hit rate, times hit rate of level 3 cache. What's that, 10 nanoseconds? That should be 7 plus 5 is 12, plus 10 is 22. And that would be why it matches 122 nanoseconds there. So this math is going to be correct. 0.18 plus times 22 nanoseconds plus 0.2 times 122 nanoseconds. Because 122 nanoseconds is 5 plus 7, to go back to an analogy with Thomas, Lee, and so Andrew. 5, ask him, he doesn't have it. I ask Lee, that takes another 7 seconds, he doesn't have it. I ask him so, that takes another 10 seconds, he doesn't have it. Now I need to go to Andrew, he gives it to me in 100 nanoseconds. Does that make sense? So that comes out to 5.503. Now, what's going to happen here, let me ask you guys a thought question. Why wouldn't we just keep adding levels of cache to keep reducing the access time? Why do you think 3 is a good choice? I'll give you a hint. Draw a graph here. So the first one was, we had 100 way up here, right? So with 0 levels of cache, we had 100. With 1 level of cache, we got it down to 10. Level 2, we got it down to 6. Level 3, we got it down to 5.5 something, right? And so the graph's going to look like that. So why do you think adding levels of cache, why there's a limit to the effectiveness of it. Why wouldn't we just add 12 levels of cash?
Because it will only move only a little bit.
Yeah, eventually you're gonna, because each one's gonna cost less and be a little slower, right? So eventually you're gonna find an asymptotic bound.
Yeah.
But then you're like each level of cash is gonna add money, right? So your money's gonna go like that. So the sweet spot tends to be this level 3 cash.
So why stop at 3 and not at 2 when the difference between 2 and 3 is like 1?
Well, I mean, if they get 1 nanosecond, but if we did a level 4 cache, we probably go down like 5.4, 5.3, level 5 cache. The asymptotic would be close to 5. So 6, you're just getting a performance of 6 over 5, right? A performance improvement of 6 over 5. But if you're adding a 4 level cache, it becomes like 5.3 over 5. So that's still kind of a significant difference. Mm-hmm. So that's like, this is 1.2, and that's not even like 1.3 fifths is what, 0.6. So this becomes 1.06. So now we're going to have performance improvement of 1.2 versus 1.06. But then the next one would be like 1.03. So that improvement is kind of negligible. Does that make sense?
I have a quick question.
Yeah.
This, so where you have 0.8, it sorts like the last 0.8 times 22 nanoseconds.
Yes.
So you have the H3 is going to be the hit rate, right?
Yeah.
Over one more. Yeah, there you go.
Mm-hmm.
And then times the cache time. So you're having to add up all the.
Correct.
Add up all the ones. Okay. So this one was 5. That one was 7, and this one's 10. And so okay. So,
Yeah.
Okay.
So this is this specific instance, right?
Yeah.
So what's happening is, as we're branching, these are possibilities. Like I got it here, I got it here. But if I get it to here, at this point, how long is it going to take me if I have this particular probability branch? In this case, it's going to be 5 plus 7 plus 10, which is 10.
I see before you wrote like H2 times TC1 plus TC2.
Yeah.
So is that just
H2 TC1 plus TC2 minus H2. This should be all of them added together. Hit rate and then the sum of them all plus 1 minus 1, 2, and 3, and then TN. It's going to go over the next line, but whatever. Okay.
makes it a little easier for me.
Yeah. Okay. Does anybody have any other questions before we move on?
So the original calculation hasn't been changed. So 0.8 times 10 plus 0.2 times 122 is 32.4. Updated to 0.8 times 22 nanoseconds plus 0.2 times 122, it's 42.
It's 42?
And the final answer is 5.5.
Just 42.0 or?
42.0, yeah.
42.0, and then what's the final answer?
5.75.
575. Thank you. Any other questions before we move on? Okay, so how do we control the miss rate of the cache? So these three, I want to warn you because I get a lot of questions whenever we go over this. Some of these are gonna seem contradictory. Unfortunately, that's life. That's compromises, right? So you do one thing, oh hey, that might increase it, but the problem is it has an impact on increasing the cache in another way. So it slows it down. So eventually you're going to have to find the sweet spot based on, those remember the 4 design principles. Make the common case fast, smaller is faster. Good design requires good compromises. Good design requires good compromises. Increase the cache size. Oh, hey, let's just make it bigger, right? Woohoo! More blocks can be kept in cache. Chance of miss is reduced. However, a larger cache can be slower. So we have a reduced miss rate because there's more in there, right? But why would you think that would be a little slower?
It takes longer to go through.
Yeah, you have to go through all the different elements to find it. So now you have difference between searching through it versus just getting the miss rate having to go to the next level. So there's compromises there. Increase the block size. So you're increasing the data transferred between back and forth. So in this case, you could say instead of transferring 8-bit blocks, we're making a word. We're going to make it 32 bits. We're going to make it 64. We're going to 128. But what's the problem? So in this case, we've increased the block size, but we maintain the same size of the cache. So what do you think the drawback is? So think of what I'm sorry, what was that? So you have to end up having fewer blocks. And what's the block size taking advantage of? Term I said at the beginning of class. Term I said will probably be on your exam. No. I mean, you'll need locality, right? We're taking advantage of locality. So if you make the block bigger and bigger, guess what? You're losing some of that locality because they tend to cluster in groups. So the bigger you make it, the more useless information you have because you have a cluster, and then if you have it's outside of that, then you have useless information that you don't need, but you still have to swap in because you still have to swap in the entire block. Because remember, the block is the minimum amount of information that can be transferred back and forth. So smaller blocks takes advantage of locality. Larger blocks would make more data available. So if you had a larger cluster, that would be advantageous. But if you have smaller clusters, then you just have wasted information, and then you reduce your hit rate because you don't have that second cluster in. And then increase the hit rate. Hit rate increases with cache size because there's more in the cache, right? However, hit rate depends on block size. So that's what we were just talking about. Hit rate depends on, if I have this in there, locality, the more blocks that I have in there that I can hit, the more likely I'm going to have it in there. So increasing the hit rate by actually, so you see how all of these kind of, oh, hey, I can just increase the cache size. Well, that doesn't necessarily work either. Oh, I can increase the size of the block. Well, that doesn't necessarily work all the time either. So there's good design requires good compromise. Remember, MIPS was a compiler-driven encoding of microvision focused on performance. So they have 3 levels of cache, 8-bit blocks, 32 instructions. They chose those to increase performance. So does this all make sense? I was just throwing a big chunk of memory hierarchy at you.
Why can't we have 2 caches in parallel?
Caches in parallel? Well, now that we would be getting into, we will discuss that issue in section 8, but it's a problem, we'll discuss an issue called cache consistency or cache coherence, same thing. So the idea is if I have 2 caches in parallel, right, what I'm going to have to do is run them on multiple processors. Well, if I'm doing multiple processors that's running the same program, right, then eventually there's going to be a point where both of the processors are going to need to share a variable. If I have parallel caches, then I need to have multiple copies of the variable in each one of those caches, right? So what happens when one processor wants to update the variable and then another processor wants to update that variable? You have to use something called dictionary protocols in the Snoopy bus, which we'll learn about in section 8, to monitor all of those parallel caches. So parallel processing and parallel caches definitely, and you'll see that you get significant improvement, but then you get into these data hazards, structural hazards, and control hazards.
So we're thinking of multiple caches in parallel with a single processor?
Yeah, but you need to just become
A larger
large
cache.
cache. Okay, that's what you were asking?
I'm not sure.
Okay, so either way, we've answered both of the questions, so hopefully you feel even twice as enlightened. Okay, and so these are diagrams showing the difference here. So then locality, this should, oh yeah, we'll go into direct and set associativity. This is where we're going to start exam 3's information, right here. So you're going to be doing a set associative, direct and set associative problem. Then we're going to be going into data path. Then we're going to be going into exceptions and interrupts. And then we'll end the course with some parallelism. We'll be discussing cache consistency, cache coherency. We'll be discussing something called Tomasulo's algorithm, where we're using floating point operations in parallel. And we'll be showing instruction level parallelism. And then pipelining. So from here, what I want to do next, let's do exam 2 review. First things first, homework is going to be 5 point, we started at 5.4, correct? I'm double checking. Yeah, 5.4 through 5.13. And then example questions.
Do we do 5.13?
I'm checking that right now.
I think we did 5.
Yeah, 5.12. Yeah, 5.13 is going to be tag index blocks and block and byte. And then example question. Yeah, well, 5.1 through 5.4. But they all build into 5.4. So 5.4 is just kind of everything works. While everybody's jotting the last couple things down, let me erase this chalkboard. I'm sure people will have questions. Okay, so what do you think is going to be on the exam?
Quiz number 2.
Okay.
Some problems off of there.
What specifically? Okay, so sign multiplication. And then you'll have a restoring or non-restoring division. Make the font a little smaller here. And it'll take up. Yeah. Just a second here. 10. Let's make this lecture for the 28th October. We'll start here. Okay, so that should be up. Means just a little bit so you guys can. Okay, so that's one thing that could be on there. What could another thing be?
Our last quiz was example 4.7 and 4.13.
Oh, we're covered on those.
It was the
Okay, convert C to MIPS assembly. And what was the other one?
Partitions.
Yeah, state minimization. problem where I'll give you some states, you'll minimize them, and then you'll do binary, and then what's the other term? One hot encoding. What else could I ask you?
TGO 5.4. Locality.
So define locality and two types. And on the exam, I'll probably say choose one for. So you actually have to explicitly state which one you're going to choose on the exam.
Either simultaneous or.
Oh no, you'll have. So I'm talking about restoring or non-restoring. So on the quiz, I gave you one of each. So on the exam, since there's other things we need to ask, you can pick restoring or non-restoring. But you have to explicitly say, I'm doing non-restoring, and I'll indicate on the exam, must write which one you're using. Okay, what else would I ask about?
Memory hierarchy.
Memory hierarchy, what specifically about it?
Example 5.4, what we just went over.
Yeah, example 5.4. So what's the term for example 5.4? So that's a
Average.
level 3 average memory access. Someone else besides Clinton? It's now in my head. Time. I'm trying to figure out an average. I'm getting to the memory. I need to access it, and I need to know how long it takes. So
would you tie that back into like 5.3? Like, would you have a separate problem?
Oh no, 5.4 is, I would say, take 5.1, 5.3, and 5.4. But you see how 5.4 is actually from example 3, and then 5.3 has tie-in from example 1. So if you mix all three of those together, there's your problem.
TGO 4.20. What's about the registers?
What about the registers?
That graph on this at the bottom where it shows you like how many bits are in like the opcode and the URD.
Oh, so you have the three. Yes, this is a potential exam problem right here. The three TGO 4.20, we have the three types of instructions. What else did we cover in section 4 that would be a potential definition problem? Since we just spent today talking about memory. Let me look up the exact number. No, it was on the one that. Here you go.
Latter one or the earlier one?
Yeah, latter one. The exact number is. Where is it? So I just talked about memory. It was right, section 4, and we did a lot of. I'm sorry, it was the beginning of section 5. My fault.
I don't know.
Beginning of section 5, we talked about memory. Before we talked about memory hierarchy. In order to find out how to get there, if I'm trying to get to someone's house, I need what do I need? Memory addressing, right? So I have the 5 types of memory addressing. Was it TGO 5.3? Oh yeah,
Which are those in?
Oh, okay. Well, here it'll be this one right here where I talk about register operand. Great, I hadn't gotten back. So 5.3, immediate, register, base addressing, PC relative, and pseudo direct.
Would you just looking for a definition?
Yeah, I'm looking for a definition in the drawing, just the exact same way Yeah, if you look at the what I have posted for the problem, I'll say state and define the 5 types of memory addressing and MIPS and draw their representation. So this is what I would expect. So I apologize for not having the TGO back to you, but to make up for it, here's the solution so you can study. Scroll, scroll, scroll. You guys have learned a couple of things this semester, allegedly. Okay, so 5.3, 5 types of memory addressing. Trying to think of what else. What else could potentially be on the exam? Lee, what do you think could possibly be on the exam? Bingo, you figured it out. That's why I was asking him. I-4 representation. So I posted the Java code. I would use that because they'll put out the exact answers. Mr. Jenkins here, not Clifton. He wrote some code in Java that actually takes in the byte representation from a float. In Java, it's a 32-bit float, which is the IEEE 754. Puts it out there. It'll show you the representations, so you can put in the values, and then it'll give you the results. And I modified it to put it out the way I want it on the exam. So if you want to practice, make up some problems. I've given you the range of acceptable values, right? So put in a problem, go, okay, this is what I expect it to be, and it'll come out and give you the exact answer. So that'll help you practice on the exam.
So for the problem, you would want us to show that progression?
Yes.
Okay.
Yeah, so there you go. So you can practice that and have that exact progression. What else could be on the exam? So we've got some computing arithmetic. Got some dressing here.
Yeah.
Wasn't so bad. So here, 4.7, 4.13. Oh, okay, yeah. Yeah, state minimization, so that's a problem. So this would be a problem. You have sign multiplication, so you've done the quiz. I'm trying to think if there's any other definitions I would ask. No, not on this exam.
Now for the sign multiplication and restoring or not restoring, will it be multiplication and one or the other?
Yes.
Or not?
So you'd have a part A here, and then a part, this would be B.
Anything about the flip-flops and the reset?
That would be you. I'm not asking that on exam because you'll be demonstrating that knowledge through BHDL project. I'm trying to keep those as separate as possible. Well, I think that's a good exam. What do you think?
Yeah.
It's pretty. I mean, it's very similar to exams I've given in the past. I mean, the answer keys for quiz 2 and quiz 3 are available. At this point, after some study, you should understand the state minimization process. You need to understand sign multiplication, restoring and non-restoring. And you're right in line with past semester performance in terms of quiz performance and then jumping up to exam performance. So I do anticipate a median of around 90 again, because you've given me no reason to not anticipate that. So, okay, well, I did want to talk about one other thing. I wanted to talk about academic integrity issues. So, you guys are submitting your project on Friday. I want to press pause here.